In the previous video, we talked about how to write a vector equation that describes this position loop, and then how to get scalar equations out of that vector equation. And of course, we had to tack on this extra scalar equation that came from the geometry of the cylinder. So we have these four equations, and we have four unknowns, which are lambda, x, y, and z. Solving this system of four equations is actually kind of tricky because it's a nonlinear system. While these three equations are linear, this equation here is nonlinear, which we can see because x and z are both squared. Solving a nonlinear system can be done using a variety of software packages, but we're going to talk about using MotionGenesis for this class. Before we get started, it's really important to point out that I have fully worked out how to solve this problem by hand before turning to the computer. The computer is simply something that can help me solve these scalar equations, but it won't help me figure out which scalar equations to solve. So when you're working on problems, make sure that you understand fully what you are solving first, and then turn to the computer and start typing. So here I have an empty text file where we'll work out the solution. Since I've already worked out the system of equations that I want to solve, I can simply define my variables, type in the equations, and solve it. So first I'll define my variables, which are x, y, z, and lambda. Next I'm going to set up a system of equations, and in MotionGenesis that's basically just declared as a matrix of equations. So we'll give it a name, like my system, and then we'll say that the first equation in this system is equal to this first equation over here. It's always implied that the left-hand side needs to be 0. So if you don't have a 0 on one side, you need to rearrange the equation so that you have 0 equals a function of other things. So here we'll type just the right-hand side. So 3 times lambda minus x minus 4. Next we'll type in the second equation, which is 2 minus lambda minus y. The next equation is just lambda minus z minus 2. And the last equation is this one here, which came from the geometry of the cylinder, which is x squared, which we indicate using the little caret here for an exponent, plus z squared minus 1. At this point, it's always good practice to try running our script and making sure we don't already have some sort of error. So as we talked about in a previous video, I'm going to run MotionGenesis from the terminal here. I'm going to change directory into my working directory, which is this fall13. I'm going to run MotionGenesis from the folder above this one by typing .. and then MotionGenesis. And then I'm going to type in my file name, which is vectorloop.txt. And there we can see it ran the file, and so far everything seems to be fine. Sometimes at this point it's nice to proceed interactively if you're not sure what to do next. What we want to do is solve the system of equations. So let's see if MotionGenesis has a solve command. And indeed it does. If we look here at the syntax lines, we can see that there are several different ways to call solve, but they all basically take a set of equations to solve and then some information about what variables to solve for. So if we run our program again, here we can proceed interactively and type solve my system and then say that I want x, y, z, and lambda. And you'll notice that it says, okay, note equation 4 is nonlinear in x, and it's asking us to enter a guess value for x. This is because in order to solve a nonlinear system, the computer is going to do an iterative guessing on the value of x and try to converge closer to a solution. So if we look back at our picture and say, well, what is x? It's the measure of the nx position of q from BO. So if we start at BO and go to Q, it looks like we're going in the minus nx direction. So let's just type in something like -1. We also need an initial guess value for y. So it looks like y is going to be some positive value. So let's pick 1. And then it needs a guess for z. And again, for z, it looks like the nz value out here at Q is probably also positive. And finally, we need a guess for lambda. So again, looking at our problem, lambda was the multiplier on the direction vector that gets us from AO to Q. So lambda is most certainly positive. So let's just enter 1 as our guess. And we see that these are the solutions it found for our system. So this is great, but let's come back over to our script here and fill it in so that we can save it. So we're going to solve my system for x, y, z, and lambda. And in order to avoid having to type in these guesses interactively each time, we can go ahead and provide the guesses in line. So over here, we're just going to say, okay, my guess for x was -1, my guess for y was 1, my guess for z was 1, and my guess for lambda was also 1. And now I should remember to actually solve my question, which was find the distance from AO to Q. So we said down here that that's finding the magnitude of this position vector to Q from AO, which will be lambda times the magnitude of this direction vector d. So we can define the direction vector, which is 3nx minus ny plus nz, and then we can define our answer, which is just lambda times the magnitude of d, which we can just ask MotionGenesis for using the getMagnitude command. Note that this is equivalent to doing the square root of the dot product of d with itself. But for now, I'll just comment this out. So before we run this, you may have noticed I didn't actually define what nx, ny, and nz are. So here, I actually need to say, okay, I have a rigid frame, it's called n. So this command will actually define those three unit vectors, and it will know that those unit vectors are orthogonal to each other. So we can come back over here and run it again, and we'll notice that it's doing something slightly irritating, which is actually trying to keep it in symbolic form. So if you actually want it to explicitly give you the result of this, we can come back over here and say, okay, what I really want is for you to explicitly evaluate this. So again, I type quit, run it again, and now it's giving me the answer, which is 3.83. So to summarize, we first worked out what we wanted to solve completely by hand, without any reference to a computer. We need to understand these position vectors, this vector equation, how to dot, and how to do this other geometric constraint to get the scalar equations that we're trying to solve. Then we can use the computer to solve our nonlinear system.